Hydroforming innovations in metal forming. Definition of hydroforming. Hydroforming is a metal forming process that utilizes fluid pressure, typically hydraulic or high-pressure water, to shape materials into complex geometries. It involves using a die to apply pressure to a tube, sheet, or other forms of metal, causing it to take on the desired shape. Hydroforming offers advantages in terms of design flexibility and the ability to produce intricate parts with high structural integrity. Issues in hydroforming. Tooling costs. Developing custom tooling for hydroforming can be expensive, especially for low-volume production. This cost can be a barrier for small manufacturers. Material limitations. Hydroforming works well with ductile materials, but not all metals are suitable. Some materials may not stand the process, limiting material choices. Equipment and maintenance. The high-pressure equipment required for hydroforming can be costly to purchase and maintain, which is a significant issue for manufacturers. Environmental impact. Depending on the hydraulic fluid used, there can be environmental concerns related to fluid disposal and sustainability in the hydroforming process. Complex process. Hydroforming involves multiple steps and requires precise control of various parameters, making it more complex compared to some other metal forming processes. Types of hydroforming. 1. Tube hydroforming. In tube hydroforming, a hollow metal tube is placed into a die, and internal hydraulic pressure is applied to expand and shape the tube. This process is often used in the automotive industry for manufacturing complex and lightweight structural components, such as exhaust manifolds and bicycle frames. 2. Sheet hydroforming. Sheet hydroforming involves the use of a sheet of metal, typically in a flat or partially preformed state, and it is shaped by hydraulic pressure against a die. This method is commonly used for creating parts with shallow or deep-drawn geometries, such as automotive panels, sink basins, and aerospace components. 3. High-pressure hydroforming. High-pressure hydroforming is a variation of tube or sheet hydroforming in which extremely high hydraulic pressures are applied to form the metal. This method is particularly suited for intricate, high-strength components and is often used in aerospace and defense applications. 4. Low-pressure hydroforming. In low-pressure hydroforming, relatively lower hydraulic pressures are employed to form metal parts. This method is commonly used for components where the emphasis is on precision and minimizing distortion, such as medical devices and cookware. Advantages of hydroforming: design flexibility. Hydroforming allows for the creation of complex and intricate shapes, including both convex and concave contours. This design flexibility is particularly valuable for producing parts with unique geometries, reduced material. Waste. Hydroforming minimizes material waste compared to traditional forming methods because it uses only the amount of material needed for the specific part. This leads to cost savings and sustainability benefits. Improved structural integrity. The uniform distribution of pressure in hydroforming results in parts with superior structural integrity. This makes hydroformed components more durable and less prone to defects. Cost efficiency. While the initial tooling costs can be significant, hydroforming often reduces production costs in the long run due to reduced material waste and improved efficiency. High strength-to-weight ratios. Hydroformed components can achieve high strength-to-weight ratios, making them suitable for applications where strength and weight are critical, such as in the aerospace and automotive industries. Tight tolerances. Hydroforming allows for the production of parts with tight tolerances and excellent dimensional accuracy, ensuring consistent quality. Reduced post-processing. In many cases, hydroformed parts require minimal post-processing, such as welding or machining, which further reduces production time and costs. Enhanced material properties. Hydroforming can enhance the mechanical properties of materials, such as increased tensile strength and reduced springback. Batch and volume flexibility. Hydroforming is suitable for both low and high volume production, offering flexibility in manufacturing. It can be used for prototyping as well as mass production. Reduced tooling changes. Hydroforming. Tooling changes are often simpler and quicker than traditional stamping processes, making it easier to adapt to design changes or produce different components. Wide material compatibility. Hydroforming can be used with various materials, including aluminum, steel, stainless steel, and even certain plastics, expanding its applicability. Reduced welding. The ability to create complex shapes in a single piece reduces the need for welding, which can improve the overall structural integrity of components and reduce the risk of defects. Hydroforming process. The hydroforming process is a versatile metal forming technique that utilizes hydraulic or high-pressure water to shape metal components into complex and intricate forms. Here's an overview of the hydroforming process. 1. Material selection. Choose a metal material based on the component's requirements. 2. Tube or sheet preparation. Prepare a hollow metal tube or flat sheet as the starting material. 3. Die setup. Place the material into a die, which defines the component's shape. 4. Fluid pressurization. Use hydraulic fluid or high-pressure water to pressurize the material inside the die. 5. Forming. The material takes the shape of the die as pressure is applied, resulting in a component with uniform thickness and minimal distortion. 6. Depressurization. Release the pressure and remove the formed component. 7. Trimming and quality control. Perform any necessary trimming and quality checks. The hydroforming process is known for its ability to produce complex shapes with high precision and minimal material waste. It's widely used in industries such as automotive and aerospace. Materials in hydroforming metals. Common choices include aluminum, lightweight and corrosion-resistant, steel, high strength, copper, brass, and even exotic alloys for specialized applications. Plastics. Certain plastics can also be hydroformed, often used in industries such as automotive and consumer goods. Material selection is based on factors like component use, strength requirements, weight considerations, and cost constraints. The chosen material's properties must align with the specific hydroforming method used, tube, sheet, or high pressure, to ensure successful component production. Question A. Copper tube of length 2 meters and cross-sectional area 4 cm² is heated from 25 degrees to 100 degrees C. If the coefficient of linear expansion for copper is 1.7 x 10 to the 5 degrees C, what will be the change in volume of the tube? Solution. The change in volume, dV, of the tube can be calculated using the formula dV RV V0 dt, where V is the coefficient of volume expansion, V0 is the initial volume, and dt is the change in temperature.